Hello everybody, I am Shusham. Welcome you all in my second lecture on linear algebra. Hope you have enjoyed my last one, that is part 1 of linear algebra, and there we have discussed about vector spaces, vector subspaces. If W1 and W2 are two subspaces of VF, then we have told that W1 plus W2 is the smallest subspace. But as I can remind, I have told about fields of all infinite fields like F may be R or C or Q. But vector space can be defined on finite dimensional field like ZP. ZP is a finite field where P is prime number. Okay? Don't always think vector space, the corresponding field is always infinite. If Vz is a vector space, what do you think? I say no, because you can check Z, the set of all integers, is not a field. Now another important note, ZP over ZQ is not a vector space where P and Q are disjoint or distinct prime numbers. Okay? Now, if V is a vector space over an infinite field F, like RQ, like this, then the subspace W is either the trivial zero space or an infinite set. Okay? So these are the notes that was missing in my last lecture, so I think to include this in the next one. Keep in mind or note it down. That will be better in your future. Coming back to the last lecture. We know W1 W plus W2 is the smallest subspace. Now, what will happen between two subspaces? Maybe they are disjoint, or maybe they have some common elements. Okay, what will be happen if they are disjoint? Let's check that. So first I will talk about direct sum. What is this direct sum? You know W1 plus W2 is the smallest subspace of a vector space V over the field F containing both W1 and W2. Now I say W1 plus W2 is the set V and they are disjoint. In that case, this is basically called the direct sum of W1 and W2, and it is denoted like this plus circle. When they are disjoint and their summation represents the complete space V. In examples you can see, in suppose V is that is xy plane. Now I consider W1 is the horizontal axis, W2 is the vertical axis, and W3 is the y equals to xy. Then V can be mentioned as W1 plus circle W2, or W1 plus circle W3, or W2 plus circle W3. Note, if these are equal, that is both are equals to V, that does not imply W2 equals to W3. When you can represent a vector space as a direct sum of two subspaces, then these two subspaces are called complements of each other. So, from this example I can say complement subspaces may not be unique. Why? Because W1, W2 are complements, similarly W2, W3 complement, W1, W3 complement, so complements are not unique. Okay? Okay. Now the vector space Mn are C, that is the set of all matrices of order n, is the direct sum of all symmetric and skew-symmetric matrices if the underlying field is R, or it's the direct sum of Hermitian and skew-Hermitian matrices if the underlying field is C. Okay. Now I consider the subspace is vector space Rx, and considering W like this, where Px such that nth order derivative at point zeros are 0, and W2 such that degree of Px less equals to n. Then we can represent the set of all polynomials, that is Rx, like W1. Here Rx is basically your PNF. V can be mentioned as W1 plus circle W2. So direct sum, now you know. What about coset and quotient space? Let's see what is coset. So you have a vector space V over the field A, you have a subspace W of Vs. Now I took an element V from the vector space capital V. What will happen to this set? Here it is. This is called the coset of W containing V. These are some properties. If this V instead of vector, if it is in W, then you know W is a subspace, so it is closed under addition and scalar multiplication. Then V plus W, it's W. So V plus W is a subspace of V if and only V is in W. Now two cosets will be equal if and only if, remind about this additive inverse, V1 minus V2 is in W. So these are some important properties. What is quotient space? You have coset. You took an element from V and then add this to all the elements of the subspace. Now the set of all cosets defined as this, and it's called the quotient space. Quotient space is a vector space over the field F under the addition and scalar multiplications are defined like this. See, C of V plus W, CV, because V is in capital V. C is a scalar. So W is a subspace, it's closed under, or it preserves the vector addition and scalar multiplication. The quotient space is denoted by this, and dimension of this dimension I'll tell you later today. In this lecture it is included, but I am going slowly about various definitions, topics to build up the definition of basis, which is very, very important. Okay. Now linear combination, that you all know. Many a times we use linear combination. Linear algebra means there must be some linear combination. What is that? Suppose you have a non-empty subset S of vector space here. It's a subset, not a subspace. Okay? If S be a non-empty subset of a vector space V, and any vector V in V can be written like this, where ui's are from the set S and ai's are scalars, then this kind of representation is referred to as a linear combination, and the scalars ai's are called coefficients of linear combination. Okay. Now V is in V, 0 is also in V. It is the additive identity. So okay, 0 is in V, and the linear combination we can written like this. Now if that coefficients are all zeros, then we call the set S is linearly independent if they are all 0. If any of them is not 0, then we call the set S is linearly dependent. Got it? Thank you. Let's go to next slide. What is there? It's tell about spanning and generates. What is spanning? You know about linear combinations. Now, the set of all linear combinations of the vectors in S is called the span of S. So all possible linear combinations and set of all possible linear combinations is called the span. Span of phi is empty set 0. Span of x-axis, y-axis contains all the points in the xy plane. Like if x, y, z, this is your 1, 0, 0, this is your 0, 1, 0, then all possible linear combination is the xy plane. Another theorem. S is a non-empty subset, as I have mentioned. It's not a subspace. But what about span S? Spanning of S is a subspace of the vector space V and it is denoted by Ls. Not only that, this is the smallest subspace of V containing S. Moreover, any subspace of V that contain S must also contain the span of S. Okay, I forgot one thing about the properties of linearly independent sets. Let's go back there. Sorry. Here. That empty set phi is always linearly independent. Any singleton set is linearly independent because you can consider this linear combination, then you will get C as 0. If V is a vector space and S1, S2 are two non-empty subset of V with the property this, then if S2 is linearly independent, any proper subset of S2, that is S1, is linearly independent. If S1 is linearly dependent, then any superset of S1 must be linearly dependent. In case of vector space like matrix, set of all matrix of order n cross n, this is linearly independent, then their transpose set is also linearly independent. Okay? Now coming back to generates. We know linear combination, we know spanning. Now generates. What is generates? Its subset is obviously non-empty of a vector space V. Generates V if span of S is V. Means the set of all possible linear combinations of a non-empty subset A represents the complete vector space V. It is possible. Suppose you have R2. Two tuples R2. This is X, this is Y. Then we can consider a point 1, 0 and we can consider here 0, 1. Then set up all possible linear combinations with 1, 0 and 0, 1 represents the whole vector space R2. So this is the generates of R2. Here I have given some examples. You can go through this like this. It's a PNF set of all polynomials with degree less than or equals to n. Then this generates PNF. Now R2, R3 are infinite. You know R is also infinite. But they are generated by some finite sets. Okay? Here that is finite. PNF, it is finite. But that is not always true. If you consider the set of all polynomials PF, then this will be generated by an infinite set. Okay. Finally, you can go through this example in matrix. There are some properties of generates I have mentioned, like this is you know already. If S1 and S2 be subsets of a vector space V, S1 subset S2 implies span of S1 subset of span of S2. If some set contains less number of elements, obviously the possible linear combinations must be a subset of the superset. Span of S1 union S2 is span of S1 plus span of S2. This is equal in case of finite union. But span of S1 intersection S2 is a subset of span S1 intersection span S2. When they are equal, that is this span of the intersection of 2 equals to span of S1 intersection span of S2, if they satisfy this condition, and that is very trivial. Okay, sorry.